part 2. So today we're going to connect what I told you about yesterday. So I was mainly talking about machines, and so I've included a recap about the first part. So what we saw yesterday, it was we discussed basically how Turing addressed the problem of defining what is a mechanical calculation. And I'm sorry that you weren't here, Renzo, but I have a few examples here. So basically, he identifies the concept of computable, so of computation, with that of a Turing machine. And what's a Turing machine? A Turing machine is a machine that can do very simple operations. So it can read strings of symbols, and it can manipulate these strings. It can do really simple actions, like go right, go left, and replace the current symbol I am looking at. And it can change its state, which is meant to be a sort of the state of mind of the machine. That's what Turing used to call it. So this was an example from yesterday's part. So this machine was multiplying any number by 10. And I'll go through it again, especially for Renzo. So the intuition is that in order to multiply any number by 10, we just read it from left to right. And as long as we see a symbol, which is any symbol really, so any number, any digit from 0 up to 9, we just move right. So we reach the end of the number, which in symbols, well, which corresponds to this line here. So whenever we hit a blank symbol, that means we hit the end of the string, representing our number. So at that point, we just write a 0, and we switch to the state SF, which means that the calculation is over. I don't know if you're are you able to follow this, Renzo, or do you want me to go back to yesterday's slides and articulate this more into depth? Or are you happy with this description? Are you here? Can you guys hear me?
Yeah.
Okay. Okay, well, I'll assume that this is okay for the moment. So this is another example program which we use to we may use to sum 1 to any number, and this was a slightly more complicated example. I'm sure you guys remember about it. So one more thing that I wanted to add about what I said yesterday is I wanted to talk about the universal Turing machine, but I didn't have the time, so I'm gonna catch up now. So basically, the idea of the universal Turing machine is that the programs that we have can be encoded themselves in the tape of a Turing machine, right? So we can basically take this program, which has a very regular, nice structure, and we can encode it on the tape of the machine. So for example, in the case of the program that adds 1 to any, that multiplies any number by 10, we can just we can encode these lines in order in this way. So we have that when we read 0 and we are in state S0, we do action write, and then we go to state S0. And the first 4 symbols here mean exactly that, okay? Then we can encode the second line. So this line here is encoded here, and so on and so forth, right? Up until the last row. And at the end, let's say we have a special symbol here that separates our program from the input. So the input is 41, let's say. The universal Turing machine is any machine that is able to simulate the Turing machine that we have encoded here, and we can run it on this input. So it will simulate a computation on this input, right? The great thing about the universal Turing machine is that you can just plug in any program. So for example, we can just encode our other program for adding 1 to any number, and the behavior of the universal Turing machine will change accordingly. So it will now simulate this Turing machine. Does this remind you of anything, like of any concept you've seen in your life, in your digital life, I would say? So so what we're doing here really is that we are writing a program in the first part of the tape, and then we have an input. And so we are using a universal Turing machine for running programs. And this is interesting because this is very similar to modern computers, right?
But sorry, can I ask you?
Yeah, of course.
You're talking about a universal Turing machine. That means that, I don't know, something like a particular Turing machine exists.
Exactly. So this is yeah, I'm just telling you that there exists a specific Turing machine that can simulate any other Turing machine.
Okay, but not programs.
So, yeah, including, so it can simulate programs. So if you write a program in the tape of this Turing machine, the universal Turing machine will behave in a way that it is indistinguishable from the Turing machine being encoded.
Okay.
Is that clear?
It's just so different level.
Yeah, so I'm using a Turing machine to simulate another Turing machine.
Okay.
This is what I'm doing. So in this case, if I plug in this, so this program into the tape of the Turing machine, eventually this Turing machine will return as its output when it reaches the final state. It will return 410. Okay, because this program multiplies any number by 10. Okay.
Mm-hmm.
If I take the same universal Turing machine and I plug in a different program, I will just so the universal Turing machine will behave in a different way. So it will simulate this new program. So at the end, we will get 42 as the output. So this is why it's called universal, because it can simulate any Turing machine. Okay. This is, I mean, it's an interesting concept, and it's the foundations of modern computers, basically. Because if you think about an operating system, for example, an operating system like Windows or a Mac OS, that's a program that can run programs. So it's very similar to that concept. Then I can just change the program and I will get a different behavior. Okay. And
okay, thanks.
You're welcome. So obviously this universal Turing machine will have a program for itself, right? It's a bit confusing. It's this meta level thinking that you have to unlock, let's say. So obviously, I mean, yeah, this is the question that Alan Turing was asking himself. So can I find a program that when I run it, it will simulate another Turing machine?
Sorry.
Yeah, no worries.
Yeah, because if the universal program and the particular program, okay, we can talk about programs or Turing machines, right? Okay, but
yeah,
are they different in a substantial way? Like they are, they have different properties. So when I'm talking about the universal one, is the one with all the properties that makes him able to understand all the other particular program, or all the programs are the same, there's just one that is at the roots of the other, so it's just I don't know, a structural hierarchy, or there is another kind of hierarchy?
No, so okay, so they are, so from the point of view, so is it clear what a Turing machine is? So when I talk about a Turing machine, I'm talking about this the tape with somebody doing these mechanical operations, right? Mm-hmm. And the program. Okay.
Yeah.
So basically, the universal Turing machine is exactly it has the same nature of all the others Turing machine.
But why do you need to duplicate the level? So if it's the same nature.
Yeah.
And I got it, but so the reflexive, the duplication makes you able to have a reflexive look at the, I don't know, the level that is under the first one, upper the first one. It's just about that, but they are all the same. So it's just that so they work in the same way.
Yeah, they work in the same, exactly in the same way. So the universal Turing machine works according to the same principles as all the other ones. So it will follow a set of rules like these ones. Okay, it's just that these rules of the universal Turing machine allow the universal Turing machine to read any program and just behave as if it was that Turing machine that is being encoded.
Okay.
Okay, so you have a, let's say, so I'm not writing it here. So Alan Turing actually demonstrated what the actual rules are of the universal Turing machine. And then he said, well, you can just give me an encoding of any other Turing machine, and this Turing machine will behave as if it was the other one Turing machine.
Mm-hmm.
Which is it's a bit strange. So they are exactly the same thing, right? But you have, on one hand, a Turing machine like this one, whose purpose is that of adding one to any number. It can't do anything else. So this Turing machine here can only add one to any number. This is its only purpose, okay? And you can call it, instead of universal, you can call it Turing machine plus one, because the only thing that it does is adding one to any number. The universal Turing machine, its, let's say, reason of why of living is that it just takes as input a Turing machine, and it just mimics its behavior. This is what it does.
Yeah, I got that. I think that my doubt was just why do we have to have a universal one able to do, I don't know, one times the plus one times the per 10. And so the advantage of the interaction of a universal one and the specific task ones,
right,
is that you can add every time you want a specific task. So you are very flexible.
So you have one machine, and you can do whatever you want with that machine. So it's basically like a modern computer, right?
Yeah.
You can just run as many programs that you want. So you can think of any laptop or any phone as a universal machine, because it can just run any software. You think of it, yeah. So like a washing machine is not a universal Turing machine, because it's programmed just for doing that, right? A universal Turing machine can do anything. It just takes data as input, and it just simulates that software. So so from let's say a practical point of view, this is the advantage of having a universal Turing machine. But the reason why Alan Turing himself wanted to find a Turing machine was that he wanted to prove a negative result, so that there are problems that can't really be solved, right? So that's the theoretical reason for doing this.
Okay, thanks.
You're welcome. So if we go back to the for example, to the liar's paradox, this sentence is false. In a way, when I say this sentence is false, the word this is referring to the very sentence, so itself. So this is the way Turing was trying to tackle the problem. So he was trying to talk about Turing machines within Turing machines, okay? And this way, he was able to prove a mathematical theorem. So he found a way so he found a problem that it was impossible for any Turing machine to solve, okay? So he so he showed a program to do this. It contained some errors, and then it was, I mean, it wasn't a substantial error, but then some other authors found a real universal Turing machine. okay, yeah, so this is exactly what I was telling you about. So this was at the heart of his main negative result, that the halting problem is not computable. Go and check it out if you like. And as I was telling you, the universal Turing machine is similar to modern multi-purpose computers, and perhaps the human mind. So this is the thing. Are we equivalent to Turing machines, to a universal Turing machines? Because we are, in some way, we are able to learn and put in practice stuff that we've learned, right? And we can tackle several tasks and things like that. So it is sort of natural to think about these questions. Are we Turing machines in a way? And there is a great talk that Alan Turing himself gave at the London Mathematical Society in 1947. And the Second World War was over at that point, and he was working on an actual universal Turing machine, which was called the automatic computing engine. And he was talking about the possible applications of these machines. But at some point, he started talking about also ethics. And I find this very interesting, because he was saying, well, this machine, which was very big, this is a replica of that machine, was very big, and it needed what he called masters and servants. So the masters were basically what today we would call computer scientists. Of course, at that time, there was no computer science, so there were no computer scientists. And he was saying, well, its masters will program these machines, basically. And they will think and find deeper and deeper ways of using it. So the master was he was a mathematician or a computer scientist. The servants were limbs, as he said. So they were just feeding the machine with cards. They were, fixing it as there were, parts going wrong. They were just, doing the mechanical stuff, right? And at some point, he started arguing, well, as time goes on, servants will be replaced by mechanical and electrical limbs. So the point he was trying to make is, well, servants aren't really, being a servant doesn't really require being creative or think. It doesn't require any thinking, any creative thinking. Okay. But at some point in that very talk, at some point he says the masters are liable themselves to get replaced. So this is a very bold statement, because he's basically arguing, well, the masters are the brains behind the machine. They are programmers. They are coming up with programs. But at some point, we will probably be able to replace mathematicians and computer scientists themselves with machines. So he was already in 1947, he was talking about artificial intelligence. And then he goes on, he says that the masters might refuse to do this because they don't want to let their job stolen. This is very funny. He was apparently he was a very funny person. From one of his PhD students used to say that. So I find this is really interesting in a number of ways. So he was really ahead of his times, and so this makes me think of linguists sometimes. I don't know if you have any friends who are linguists, but it happens to me sometimes that I talk to my friends and they tell me, oh no, automatic translation and Google Translate are just bullshit. They will never match human performance. Which is, I mean, it's true to some extent, but I think Alan Turing was talking precisely about that sort of reaction. People don't want their jobs to be stolen. So, you know, linguists that don't really want to be replaced with machines. And that sort of reasonable. So then in 1950, Alan Turing again introduced the imitation game, which you may have heard of. I'm not gonna talk about it explicitly because it's now become part of the pop culture. But I'm going to refer to it in an implicit way later on. So this paper, I don't really, so I'm not going to tell you everything about this paper because I find that it's a really interesting read. So I just want to get you intrigued. And I want to well, maybe check it out and try to read it. So what I'm gonna do is I'm gonna show you some of the objections that Turing was aware of at that time that people could have against artificial intelligence and the use of Turing machine as a replacement for the human mind. And he listed an incredible number of objections. So I think these are 8 or 9. Yeah, 9. 9 objections, and I'm gonna read some bits of this paper with you guys. So he started off with the theological objection. At the beginning, I wanted to present you the objection and some parts of Alan Turing answers, but then I thought that you might want to check them out yourselves. So I'm just gonna present you with the objections, and then I'm gonna tell you why I personally disagree with all of these. But I wanted you to see them at least. So the theological objection is quite an obvious one. So thinking is a function of a soul, not of a machine, right? I think this is well, this is still a very reasonable objection. Probably I don't know, I will at the end when we've seen them all, I will ask you to tell me what you think is which one you think is the strongest objection. The heads in the sand objection. The consequences of machines thinking would be too dreadful. Let us hope and believe that they cannot do so. He was kind of being witty and very. I don't think he was being too serious when he was talking about these objections. But yeah, I prompt you to read his answers to these objections. The mathematical objection. So there are a number of results of mathematical logic which can be used to show that there are limitations to the powers of discrete state machines. So we've just seen one of these results, right? So I've told you that it is possible to find some problems that cannot be solved by a Turing machine. And during the years, people have argued that human minds in some way can solve these problems, which is a weird, I've always found it a weird statement and a confusing one. So some people said that basically that people can solve the undecidable, can decide the undecidable, which is sounds a bit strange, right? But this is also a very popular argument. Later on in the paper, he says also that, so he's saying in this part that there are many results of this kind. I was mentioning a few of them. He said, well, there are results due to Church, Klein, Rosser, and Turing. He was talking about himself, obviously. And he says, well, the latter result is the most convenient to consider since it refers directly to machines, which is very interesting because he's basically saying that his negative result, in a way, is more apparent than the others. It's more easily understood by people because the other results were highly mathematical. They were laid out in terms of logic very often. So they were logical arguments in a form that was very similar to what Paolo was showing you. So that's kind of harder to, it's harder to see the link between what Paolo showed you and its direct link to a decision process. So a computation. Whereas in Alan Turing's machine, the connection to computation, to deciding things, taking action is more direct. So in a way, he was saying, well, he was admitting that his result was kind of more accessible. And this is what made, I think, Turing's ideas very popular and very fruitful. Then we have an argument from consciousness. So he is citing somebody else, so Jefferson, but he says, well, some people say that I won't be convinced that a machine is really able to to be intelligent until I see a machine writing a sonnet or doing something emotional, right? Or telling me about the emotion it feels, or I don't know. Yeah, so have feelings basically, and be self-conscious. This is a really interesting point, I think. The argument from various disabilities is that so he was talking about people saying, I admit your machines can do this, can do that, but I've never seen any machine able to do X, where X can be any of these things, like be kind, resourceful, beautiful, friendly, have initiative, have a sense of humor, tell right from wrong, make mistakes, fall in love, enjoy strawberries, and so on and so forth. So this is another argument against artificial intelligence. Then we have what it is known as Ada Lovelace objection. So Ada Lovelace, again, the first programmer in history, in one of her notebooks, she says that the analytical engine, which was the machine that Babbage was building, has no pretensions to originate anything. So it's not really creating anything new. It can do whatever we know how to order it to perform. So we are the masters, and the machine is our slave, and we command it to do some stuff that we order it to perform. But it can't really originate anything. Argument from continuity in the nervous system. So, well, yeah, the nervous system is certainly not a discrete state machine. So it has neurons and connection of neurons. It's a really complicated system. How can you mimic such a complicated system with a discrete state machine? And I think this is easily one of the arguments that some people with a medical background would have. And I think this is one of the strongest ones, probably. The argument from informality of behavior. Well, this is, well, if a machine was intelligent, it should be able to capture within its rules, so within its program, all the possible conceivable behavior under all the possible set of circumstances. So obviously, if you see a red traffic light, you stop, but what happens? So how do you deal with situations where the behavior is not directly encoded in the rules guiding your algorithm? How do you do that? And yes, he says, I agree with all of this. So it's a good argument. But then again, from this, it is argued that we can't be machines. And again, he says, well, at the end, he says, this is too strong of a consequence. So he's trying to make, all these are good arguments, but they make appeal to the intuition rather than proving anything, right? Then he also had the argument from extrasensory perception, but I don't really think this is worth talking about because we've already dismissed extrasensorial perception as bullshit. Can I say this? I don't know if I can say this, but years and years ago. So that's yeah, let's not talk about this. So one of the strongest arguments against artificial intelligence, and one of the most popular ones, is the Chinese room. I don't know if you've ever heard about it. It's become super popular, and have you not? Never. Never ever. So sorry, I'm missing a citation here. There is, I will put it in the slides when I upload them. But the idea behind the Chinese room is that, well, this idea is by John Searle, who's a philosopher. So let's say that we have a room. It's this square here, big square. And there is a non-Chinese speaker inside this room. Okay. So a person. This person doesn't know anything at all about Chinese. But then he has a program, so like a Turing machine. So imagine that he has a set of rules, more in general. So yeah, that's a program in the form of, you know, an infinite, well, many sheets of paper. And this program allows him to simulate a conversation with somebody who's Chinese. Okay, so he can just follow the rules on this piece, on the paper, written on paper, just mechanically, because that's the definition of a Turing machine, right? The definition of an algorithm, of a mechanical calculation. It's something that you can do without any thinking, without requiring any thinking. So he says, well, the non-Chinese speaker then would be able to follow these rules and simulate a conversation with a native Chinese speaker who's outside the room and who's giving him or her Chinese messages. So he's taking these messages from the outside of the room. So he's receiving these messages from the outside. He's elaborating them using the program. And he's using this program to compile a letter that then he sends out to the native Chinese speaker. Since the program inside the room, we are assuming it's this program can simulate a perfect conversation, like is indistinguishable from so makes the person using these rules indistinguishable from a native Chinese speaker. Basically, this person outside the room will not notice that the person inside the room is not Chinese. Probably this person will think that the person inside the room is Chinese, right? Because they're having a conversation in Chinese. It's just that this person doesn't know Chinese, right? So he's saying that, so from this, John Searle says that, well, having a program to speak perfect Chinese doesn't require being, in a way, doesn't require knowing Chinese. So, and being sort of aware of this knowledge. So, because this person doesn't know anything about Chinese, he's just following some rules. Do you follow this? So he's saying the point is, this person isn't aware of anything, of what's happening. He's just using a program. So having a program to speak perfect Chinese doesn't make the person inside the room a Chinese speaker. So this is a strong objection against against artificial intelligence, because here we are distinguishing between being a Chinese speaker and having a program to speak perfect Chinese. And he's saying, well, these two things are different. Okay. It's a bit of a tricky concept. But then this, so John Searle thought, well, I have a proof. So when he came up with this argument, he thought, well, I came up with a proof that artificial intelligence is impossible. And he said, well, artificial intelligence is impossible in the strong sense. So in the sense that we can't really have computers that are self-conscious. We obviously can have computers that show some features of intelligence. And that's, he dubbed that type of AI weak AI. So you can have weak AI, you can have computers that play chess, but you cannot have computers that are self-conscious of playing chess. And this is a strong argument against artificial intelligence. I think that a really good how to say, exemplification of all the critiques to AI is hypercomputation. So since there are people who think that human brains are able to compute the things that are not computable, there were some people who said, well, I came up with a slightly modified version of a Turing machine that is able to solve unsolvable problems. Okay, and this is more or less how their argument usually proceeds. So in the previous lecture, I told you about and in this lecture as well, I told you about the Turing machine, and this is how we defined what problems are solvable, right? So we define a problem as solvable mechanically if we have a Turing machine that solves it, so that maps an input to an output. And this Turing machine has a program here inside. Okay. Now, these people who believe in hypercomputation say, well, let's assume that we have a special Turing machine that, for example, can perform an infinite number of steps in finite time. Then this, I mean, clearly, this Turing machine is more powerful than regular Turing machine because it can do infinite steps of computations in a finite amount of time. From this fact, these people usually derive the higher level consequence that now these machines are able to solve uncomputable problems. So they are, because they are more powerful than regular Turing machines. But the fact that they are solving uncomputable problems is kind of tautological, because so these machines are able to solve uncomputable problems because they are assuming these machines can solve uncomputable problems in the first place when they say that they can perform infinite steps in finite time, which is an impossible thing to do. Or, well, I mean, yeah, I would agree that this would be a good argument if they showed me a Turing machine that was able to perform infinite steps in finite time. But they never showed a Turing machine like that.
So sorry, this hypercomputation hypothesis is just based on thought experiment, like imagine a machine which is able to.
Exactly. Okay. So they're saying, imagine a machine that is able to do infinite steps of a regular Turing machine in finite time. So they are imagining that.
Okay.
And they never. I mean, we've never seen one really. We've never observed one. So I mean, this argument, I think it exemplifies very well the line of reasoning behind most of those objections to artificial intelligence as well. So in order for these objections to work, even the theological objections, right? You have to prove me that your assumptions are true in the first place. And then we can talk about it. But otherwise, this is no science. It's just, I don't know, talking. So actually, the person who came up with this, with one of these hypercomputational models, is Hava Siegelman. And she was thinking about brains because many people are convinced that our brains are models of a super Turing machine. So they are a hypercomputational model. But so she's a really serious scientist. She is very prominent, especially in machine learning. But I don't think that this bit of her research is particularly interesting. But anyway, this is a matter of taste, right? So moving on. So talking about brains, I want to show you a specific formalism that can be interesting for you for one reason, because it's a great example of applied mathematics, and applied mathematics for studying the connection between computers and the human brain in a way. And these two people are Warren McCulloch and Walter Pitts, who were very oddly a neuroscientist and a logician, and they were collaborating. And they wrote a paper which is basically impossible to read. It's this one, a logical calculus of ideas immanent in nervous activity, from the 1943. So we're always talking about, you know, the hot decades of computer science, and the so why? Well, I guess that the reason why it's very difficult to read is because they were using a very, very strange formalism. So I recommend that if you want to know more about it, you read one of the papers that I put in the references. There is one by Gualtiero Piccinini, which is a fair summary of this paper. Also, Paolo recommended to me this this article that you can find online. So I will just I put it in the slides, and you can check it out later on. And its title is quite pretentious, "The Man Who Tried to Redeem the World with Logic," but it's really interesting, and it's about the life of Walter Pitts. But anyway, check it out if you have the time. So the idea of McCulloch and Pitts was to take inspiration from the from neurons, which have well, I guess that you all know more or less how they work. Well, I don't want to say anything wrong here, given that we have people who are more informed than me. But anyway, so this is a really exemplified neuron with dendrites and an axon. So we're gonna. So the dendrites is where neurons collect the inputs coming from other neurons, and then it communicates to other neurons using the axon, if I'm not mistaken. So basically, McCulloch and Pitts had this idea. Well, let's try to simulate neurons in this way. You can see already that this thing here kind of looks like a neuron, right? It has dendrites and an axon and a soma here. Okay. And their model was very, very simple. So it could take two inputs. So let's say that we are receiving something from other neurons here. So there are some other neurons connected here in X1 and X2. And Y1 is the output. So once we collect these two inputs somehow, we'll see why, we will see how. And then we give an output, Y1. How do we do that? They were sort of inspired by the neurophysiology of the neuron. And then they said, well, if the input is so if I receive a strong input, an input that is strong enough, then I will, this neuron will fire. So if we imagine, if we think of x1 and x2 as variables that can take value in the interval 0, 1, well, let's assume, sorry, that they can either take 0 or 1. We can have 4 combinations, so both 0, 1, 0, 0, 1, 1, 1. And then I can put a threshold here. I misspelled it, but anyway. So I can say, well, if I get, if these two numbers, if their sum exceeds some threshold, then I will also fire. So then my output will be 1, and it will be 0 otherwise, okay? So let the threshold be 1. Let's say we have 1. So what's the output going to be in these cases? You can already tell that this looks a lot like what Paolo has shown you today, right? So we have input variables, 1 output variable. So this looks pretty much like a gate, a logical gate. But instead of having a logical operation, we are just thinking, well, let's sum up these two numbers. If they exceed 1, then we have a 1 here. So obviously, what do you expect this to be, for example? Any ideas?
A 0?
Yes. So where do you expect? So is, well, I should say greater or equal than 1.
Okay,
so what do you expect this to be?
1.
1, 1, 1, right?
1, 1, 1, yeah.
Great, okay. So this is what you get. Let the threshold be 2. I'm sure you know how to do this. This is what you get, right? If you fix your threshold to 2. Then they started thinking, so they were thinking about real neurons. So they thought, well, I might even have negative numbers. So let's say that I'm having a negative, so one of these inputs is an inhibitory input. So instead of being added to the other number, is actually preventing the other output from doing whatever the other output wants to do, right? So it's sort of canceling out the result from the other input. So they started thinking about more and more complicated models. So in this case, well, let threshold be 0. What can we do? Well, we can have this type of behaviors. Okay, so because if the threshold is 0, then these two sum to -1, which is less than 0, and so this is a 0. 1 plus 0 is 1, so we get a 1 as an output. 1 minus 1 is 0, so we still get a 1. Okay, this is another operation. You can tell so one of them was a logician, right? And that took inspiration from truth tables, really. Now, I wanted to ask you, for what value of threshold we get the following table. You can think about it for a So how do we get a behavior like that? Can we
No, it's impossible now. We need something more than the threshold.
Exactly. So this is the point. This is impossible to do. The funny thing is that McCulloch and Pitts themselves were aware of the fact that it was impossible to do anything like that in the using a single neuron. Okay. This is what we call a XOR function, right? So this is true. The output is true when at least one of these is a 1, but not both. Okay. So the XOR function is impossible to simulate using a single neuron, but we can obtain a XOR function if we consider more complicated networks of neurons. Okay, so this isn't really a problem at all, right? Because we're not expecting that to happen for a single neuron. I mean, even in logic, that's one of the reasons why we compose expressions and we put them together, because we want to model all possible functions, Boolean functions. So I mean, if you see this small network of simplified neurons, these neurons already had all the mechanisms that are present in modern neural networks, the ones used in machine learning, the ones that you often hear people talking about. So because if we go back, what would the next step be? Well, let's assume that these values here aren't just 0 or 1, but we can modulate them, right? So modern neural networks basically differ from these ones. I mean, I'm simplifying, obviously, but basically they allow any real number between 0 and 1 to be a possible value for x and for x1 and x2, let's say. Okay. So already we have all the elements here, and actually there is they already were aware that you could learn stuff using these networks. So the reason why neural networks nowadays are very popular is because they can learn things. Because imagine that you have some input and you know that you want, for some input, you as a human, you know that for some input, you want an output, a given output of y3. Okay. Let's say that you initialize these thresholds at random. Okay, you just put random numbers here. Okay, and let's say that you get a so you give it an input, then you collect an output at the other end, and then you confront it, you compare it to what you would expect to get usually. So you say, well, y3 is 0, but I would expect that to be a 1. So what can you do? You can go back and change some of these thresholds so that your expectation is matched by the output of your neural network. So what modern neural networks do is precisely this. So they change the threshold, they update the thresholds when they compare it, when they are given new information that, for example, is already labeled, so they know what's the expected output. And so you can use them you can use this information to update all the thresholds. So the idea now is that one of these people later on in 1958 took this idea and extended it so that a single perceptron, that's what they called it, could actually work for the XOR function. And that was, I mean, that is great, right? Because you have now you have a single unit that can do the XOR function. Fine. So in a very, very influential book, these two guys, Minsky and Papert, especially Marvin Minsky, was a super important scientist in artificial intelligence. They wrote a book which is known as Perceptrons, and they analyzed perceptrons and to some extent networks of perceptrons, but they found some other problems with them. And so some other problems like the XOR. They found some other things that could not be computed by a single unit. And some small combination of neurons or of perceptrons couldn't solve either. So this is one of the reasons that contributed to the fact that from 1969, artificial neural networks were just, somebody talked about the death of neural networks at that point, because they thought, well, that there's no use for these. Let's just use logic, which looks more how to say, more general purpose, more looks more powerful. It looks more yeah, we can do so much more with it. So at that point in time, people started using especially logical AI, logic AI based system. And this has been the situation until, because we buried this idea until kind of a few years ago. I remember that when I was when I was doing my, at least my bachelor degree, so in 2010, nobody was talking much about neural networks, and now all of a sudden they've become extremely popular. So with this, actually, I am done.